Hello everyone, welcome to the video lecture of this course finite element method. So this is the continuation of the fourth module, and in the earlier module we have discussed the two-dimensional elements considering the vector problems. Now here we we have already discussed in case of the axisymmetric element the shape function, then the concept of the stress strain relationship matrix, then strain displacement matrix, and the formulas associated with those we have already seen in the last lecture. And there we have seen different formulas regarding all these different terminology. Now in this lecture we will discuss the element stiffness matrix and the Galerkin approach, and we will also consider the temperature effect, and based on these different thing we will discuss different numericals. And okay, so let us start today's lecture. So these are the course objectives and course outcomes of this subject finite element method. Next, it is the COPO mapping for this subject. So we will start from this slide number 4. So here you can see that the assemblage of the element stiffness matrix K. We will start from here. So in case of the one-dimensional and two-dimensional elements that we have discussed in the earlier modules, there we have discussed the concept of the stiffness matrix and the formula based on which we have discussed several numericals for the one-dimensional and two-dimensional scalar variable problems. Now, here in this two-dimensional vector variable problems, again we will discuss the element stiffness matrix formula, and the basic formula for the stiffness matrix K, it is the integration over the volume V, then the B transpose D matrix multiplied by B matrix dV. So that means it is B transpose D and again multiplied by B integration over the volume V dV. So that means it will be ultimately V. So in case of this axisymmetric triangular element, this V equals to 2 pi r A. So that means the volume, it is 2 pi r A, so we can put that value here. So the stiffness matrix K equals to 2 pi r A multiplied by the B transpose D matrix, again the B matrix. So this is the formula of the stiffness matrix in case of this axisymmetric triangular element. Here the coordinate are, this is r1 plus r2 plus r3 divided by 3. So why we have considered this one? Because in case of, we know that an axisymmetric solid is actually generated by revolving a plane figure about an axis in the plane, and here we are considering the cylindrical coordinates which are r theta z. So the coordinate r, it is now r1 plus r2 plus r3 by 3, where A is the area of the triangular element equals to half into B into H, and B matrix, it is the strain displacement matrix. And the formula for this B matrix we have discussed in the last lecture. Now this is the formula that we have again represented here mathematically. 1 by 2 IC multiplied by A1 matrix, where different parameters are here in terms of alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, and gamma 1, gamma 2, and gamma 3. And these parameters are represented in terms of R1, R2, R3, Z1, Z2, Z3. So this formula we need to remember to solve different numericals based on this two-dimensional vector variable problems. Again, the coordinate z equals to z1 plus z2 plus z3 by 3, where D matrix, it is the stress-strain relationship matrix, and the formula for this D matrix, it is E by 1 plus B into 1 minus 2B, which is new also, you can say. That is the Poisson's ratio actually, multiplied by a 4 by 4 matrix, where E is the Young's modulus and this B, it is the Poisson's ratio. So these two formula for the strain relationship matrix and the strain displacement matrix, that is for B and D, we need to remember so that we will be able to solve different numericals. Next we will consider the temperature effects. So when actually the free expansion is prevented in a axisymmetric element, the change in temperature, it causes stresses in the element. Now let delta T be the rise in temperature and alpha be the coefficient of thermal expansion. The thermal force vector due to rise in temperature is actually given by Ft, this is B transpose D, then Et multiplied by 2 pi Ra, which is actually the volume. Now, so this is our equation number 4.47. Now, for any axisymmetric triangular element, the thermal force vector, that is Ft, this is actually a column matrix, consists of F1u, F1w, F2u, F2w, F3u, F3w. So this is the thermal force vector in case of any axisymmetric triangular element. And the thermal strain, it is Et, this is alpha delta, a column matrix of alpha delta T 0 and alpha delta T. So this is the thermal force vector and strain considering the temperature effects in case of the axisymmetric triangular element. Next we are having the Galerkin approach. Now the virtual displacement field, this is actually given by phi, this is equals to phi r and phi z of the cylindrical coordinate, this is the column matrix. Now the virtual strain, its formula E phi, this is equals to a column matrix of del phi r by r, then del phi z and del phi r del z plus del phi z del r. This column matrix, it is the formula for the virtual strain. Now for the axisymmetric problems, the Galerkin's variational form, it is actually given, or the mathematical representation is the equation number 4.48, which you can see here. Now in this equation, the first term representing the internal virtual work. So we can write the internal virtual work, it is 2 pi integration over the area sigma t E phi r dA. So this is the internal virtual work. Here we need to put the formula of the stress, which is actually sigma, this is equals to u multiplied by B and D matrices. So here instead of the stress we have entered the formula, then multiplied by E phi multiplied by RdA. So that means 2 pi integration over the area ut bt d multiplied by E phi into RdA, because the D transpose, this is actually equals to D. After several steps we have done performed the integration part, and we have considered if I this is equals to b into psi, where psi is the arbitrary nodal displacement. Now considering all these parameters, the internal virtual work, it can be represented by the equation number 4.49. Now this internal virtual work equation, this is in the form of ut k matrix multiplied by psi. So if we compare these two equations 4.49 and 4.50, then we can see that the formula of the stiffness matrix K, this is 2 pi Ra multiplied by B transpose, then T matrix and B matrix. So this is the formula for the stiffness matrix in case of the Galerkin approach. This formula also we need to remember to solve the numericals. So till now in this lecture we have discussed the assemblage of the element stiffness matrix. So there we have written the formula of the strain displacement matrix, which is this B matrix. Now for that we need to remember the value of the alpha 1, alpha 2, alpha 3, then beta 1, beta 2, beta 3 and gamma 1, gamma 2 and gamma 3. Next, for the strain relationship matrix, that is the D matrix formula we have seen, which consists of the Young's modulus and Poisson's ratio. So this formula also we need to remember. Next, considering the temperature effects, we have seen the thermal force vector, and for the axisymmetric triangular element, the formula for the thermal force vector in the strain we have seen here. Next, in case of the Galerkin approach, the formula for the internal virtual work and the formula for the stiffness matrix we have discussed just now. Now let us discuss one numerical based on all the concept of this axisymmetric triangular element. So what is given in this question, it states that the nodal coordinates for an axisymmetric triangular element are given, like R1 is 10 millimeter, Z1 is 10 millimeter, then R2 is 30 millimeter, Z2 is 10 millimeter, R3 is 30 millimeter and Z3 is 40 millimeter. Now we need to evaluate the B matrix for that element. That means we need to calculate the strain displacement matrix here for this axisymmetric triangular element. Now the formula to calculate the strain displacement matrix or the B matrix, it is actually represented here as equation number 1. So here you can see the B matrix, it is 1 by twice A multiplied by a matrix which is actually a 4 by 6 matrix, which consists of alpha 1, beta 1, gamma 1, then alpha 2, beta 2, gamma 2 and alpha 3, beta 3 and gamma 3. Now first we need to calculate the area of this triangular element. The formula to calculate the area of the triangular element, it is actually half multiplied by a 3 by 3 matrix, which is actually 1 R1 Z1, 1 R2 Z2 and 1 R3 Z3. So if we put the value of this R and Z, that is the nodal coordinates which are given here in this question, so we can put the value for this R1, R2, R3, then Z1, Z2, Z3, and finally we can calculate the area of this triangular element, which is 300 millimeter square. And next we need to calculate the R. that is R1 plus R2 plus R3 divided by 3, which is coming as 23.334 millimeter. Next, the value of Z we need to calculate, which is the formula, that is Z1 plus Z2 plus Z3 divided by 3. So if we put the value of Z1, Z2 and Z3 from the numerical, because the values of this Z1, Z2, Z3, these are given in the numerical, so we are getting the value of Z is 20 millimeter. Next, we need to calculate the value of alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, and gamma 1, gamma 2, gamma 3. Now the formula for alpha 1, it is R2 Z3 minus R3 Z2. So if we put the values of this R and Z, then we can calculate the value of alpha 1, which is 900 millimeter square. Next, the formula of alpha 2, it is R3 Z1 minus R1 Z3. So if we put the values of this R and Z, then we are getting the alpha 2 is minus 100 millimeter square. Next, in case of alpha 3, the formula is R1 Z2 minus R2 Z1. So after putting the values of this R and Z, we are getting the value of alpha 3 is 200 millimeter square. Next, in case of beta 1, the formula is Z2 minus Z3. So the value of beta 1 is actually minus 30 millimeter. Next, in case of beta 2, it is Z3 minus Z1. Then the value of beta 2 it is coming as 30 millimeter after putting the value of Z3 and Z1 here. Next, in case of beta 3, the formula is Z1 minus Z2. So as both the Z1 and Z2 are 10, so the value of beta 3 is 0. Next, in case of gamma 1, it is actually R3 minus R2, so the value of gamma 1 it is 0. Then in case of gamma 2, it is R1 minus R3, which is coming as minus 20 millimeter, and in case of gamma 3, we are getting R2 minus R1 as 20 millimeter. So all the formula for this alpha 1, alpha 2, alpha 3, then beta 1, beta 2, beta 3, and gamma 1, gamma 2, gamma 3, we need to remember. Otherwise, we will not be able to calculate the strain displacement matrix. Now, if we calculate this alpha 1 by r plus beta 1 plus gamma 1 z by r, then we are getting the value as 8.571 millimeter. Next, we need to calculate alpha 2 by r plus beta 2 plus gamma 2 z by r, which is coming as the same as 8.571 millimeter. And in case of alpha 3 by r plus beta 3 plus gamma 3 z by r, it is also coming as 8.571 millimeter. So next, we need to put all these values that we have calculated just now in the formula of the strain displacement matrix. After putting all these values, we are getting the strain displacement matrix B, which is represented here. So this is a 4 by 6 matrix. So what we have done here to calculate the strain displacement matrix, let us move back to the earlier page. This is the formula, that is the equation number 1. It is the formula of the strain displacement matrix, which is a complicated formula, but here first we need to calculate the value of the area. Now the formula to calculate the area of this triangular element, it is half multiplied by this 3 by 3 matrix. So here, putting the values of this R1, R2, R3, Z1, Z2, Z3, we can calculate the value of the area for this triangular element. Next, we need to calculate the values of this R and Z. So to calculate these coordinates R and Z, we need to use this formula, that R equals to R1 plus R2 plus R3 by 3, and Z equals to Z1 plus Z2 plus Z3 by 3. Next, to calculate the alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, and gamma 1, gamma 2, and gamma 3, we need to remember the formulas for all these terms. Then, putting the values for all these terms, we have calculated all these different parameters, and finally we have put the values in the formula of the strain displacement matrix. So this is the procedure with the help of which we have calculated the strain displacement matrix B. Let us calculate one or discuss one more numerical. The nodal coordinates for an axisymmetric triangular element are given as R1 is 20 mm, Z1 is 40 mm, R2 is 40 mm, Z2 is 40 mm, and R3 is 30 mm and Z3 is 60 mm. Now we need to evaluate the B matrix for that element. So this B matrix, it is actually the strain displacement matrix. Now the formula for this B matrix, which is the strain displacement matrix, it is represented here, is equation number 1. It is 1 by twice A multiplied by this 4 by 6 matrix. Now here we need to first calculate the area of this triangular element. So how to calculate the area of this triangular element? For that we need to use this formula, which is half multiplied by a 3 by 3 matrix. And this 3 by 3 matrix, it is actually 1 R1 Z1, 1 R2 Z2 and 1 R3 Z3. So if we perform the matrix operation, and after that if we put the values of this R1, R2, R3, Z1, Z2, Z3, then we are able to calculate the value of the area for this triangular element. So this is the process based on which, based on this formula, we have calculated the area of this triangular element. Now we need to first calculate the value of R and Z. So the formula to calculate the value of R, it is actually R1 plus R2 plus R3 divided by 3. And what are the values of this R1, R2 and R3? So in this diagram itself, we can see, or in the question, the value of R1, R2 and R3, these are given as 20, 40 and 30 millimeter. So we need to put this value of R1, R2 and R3 here. So finally we are getting as 90 by 3 millimeter, which is actually 90 millimeter, which is actually 30 millimeter. 90 by 3 millimeter, which is 30 millimeter. Next, to calculate the value of Z, the formula we need to use, it is Z1 plus Z2 plus Z3 divided by 3. Now what are the values of the Z1, Z2 and Z3? Again, let us move to the earlier page. So here the value of Z1, Z2 and Z3, these are given. Now we are getting here 140 by 3 millimeter, which is 46.667 millimeter. So we have calculated the values of R and Z. Now we need to calculate the values of this alpha 1, alpha 2, alpha 3, then beta 1, beta 2, beta 3, and gamma 1, gamma 2, and gamma 3. So the formula for this alpha 1, it is R2Z3 minus R3Z2. So this is coming as alpha 1 is 1200 millimeter square. Then the formula for alpha 2, it is R3Z1 minus R1Z3. So after putting the values of this R3Z1, R1Z3, we are getting the values of this alpha 2, it is coming as 0. Next, to calculate the value of alpha 3, we need to use the formula. which is R1 Z2 minus R2 Z1. So the value of this R1, R2, Z1, Z2, these are actually given in the numerical. So you can put the value of this variables or the nodal coordinates here, and we can calculate the value of alpha 3, which is minus 800 millimeter square. So till now we have calculated the values of alpha 1, alpha 2 and alpha 3. Next we need to calculate the value of beta 1. So the formula for beta 1, it is Z2 minus Z3. Now the value of the coordinate of Z2, it is given 40 and Z3 is given 60. So beta 1 is coming as minus 20 millimeter. Next the formula for beta 2, it is Z3 minus Z1. Now Z3 is given 60 millimeter and Z1 is given 40 millimeter. So the formula for beta 2 we are getting is 20 millimeter. Next the value of beta 3, it is Z1 minus Z2. Now the values of Z1 and Z2, these are 40 millimeters, so the value of beta 3 is finally coming as 0 millimeter. Next the value of gamma 1, it is R3 minus R2. Now, R3 is 30 and R2 is 40, so gamma 1 is coming as minus 10 millimeter. Next gamma 2, it is R1 minus R3. So R1 is given as 20 and R3 is given as 30 millimeter. So the value of gamma 2 we are getting is minus 10 millimeter. Next for gamma 3, the formula is R2 minus R1. Now the value for R2 it is 40 and the value of R1 it is 20. So finally we are getting the value of gamma 3 as 20 millimeter. Now first we need to calculate the value of this alpha 1 by R plus beta 1 plus gamma 1 Z by R. So putting the values of alpha 1, beta 1, gamma 1, R and Z in this equation, we have calculated the value which is coming as 4.444 millimeter. Next we need to calculate the value of alpha 2 by R plus beta 2 plus alpha 2 plus gamma 2 Z by R. Now here putting the values of alpha 2, beta 2, gamma 2, R and Z that we have calculated earlier, we can calculate this equation which is coming as 4.444 millimeter. Next we can calculate the value of alpha 3 by R plus beta 3 plus gamma 3 Z by R. Now putting all the values of this R, Z, alpha 3, beta 3 and gamma 3, we can calculate this value which is coming as 4.444 millimeter. Now if we substitute all the calculated values for the different parameters, like for the area of the triangular element, then beta 1, beta 2, beta 3, then gamma 1, gamma 2, gamma 3 and all the other things, if we put all those values in the formula of the strain displacement matrix beta B actually, then after the matrix multiplication we are getting the final form of the strain displacement matrix B. So this is the form procedure to calculate the strain displacement matrix. So what we have done to calculate the strain displacement matrix B, we have first written its formula, and there one by one we have calculated the parameters which we need to put there. So first we have calculated the area of the triangular element, then we have calculated the value of R, which is R1 plus R2 plus R3 by 3, then we have calculated the value of Z, which is Z1 plus Z2 plus Z3 by 3. After that, one by one we have calculated the values of alpha 1, beta 1, gamma 1, then alpha 2, beta 2, gamma 2 and alpha 3, beta 3 and gamma 3. Next we have entered all this calculated value in the formula of the strain displacement matrix B. So this is the end for this lecture. These are the topics like the calculation of the element stiffness matrix, then the calculation of the temperature effects, considering the temperature effects, and the concept of the Galerkin approach. And considering this theory, we have discussed two different numericals where we have calculated the strain displacement matrix. So this is the end for this lecture, and in the next lecture we will discuss how to calculate the stiffness matrix for axisymmetric elements.